see what this is going to look like in sort of equation form. So we want to define the Riemann sum, and the way we're going to use it is to approximate an area under a curve y equals f of x using n is the number of our rectangles and c sub I is some value in the base of the rectangle, and we'll see how that works in a second, as a sample point. We're going to plug these values into our function to get an approximation of the height of the function over that subinterval. And so the basic idea is right here. Each rectangle we put under the curve or onto the curve, we're saying we'll be approximating the area under the curve for that interval. And we're just using the area of a rectangle, which is length times width. Our width will always be the same. We'll look at how to compute that in a second. We'll call it delta x. And our height will always be taking some sample point in our subinterval, so there'll be some value c sub I in here, plugging it into our function, and then just multiplying the height times the width, or the length times the width, or however you want to think about it. After we do that, the area of the whole span under the curve will be computed by taking the area of rectangle 1, adding it to the area of rectangle 2, and so on until we use however many rectangles we're using. We'll add all the rectangles up, and that'll be our area approximation. This is the same thing in summation notation. And we'll talk a little bit about this more after we cover Riemann sums. I want to say a little bit about the c sub I. These are our sample points. And it turns out you can use any c sub I you want to as long as they're in the subinterval. So if we pull this picture onto the screen, here's rectangle 1, rectangle 2, rectangle 3, 4, 5, and then some kind of, we don't know how many we're using, so there's some spacing, and then the last one, the nth one. So we're going to start with A, end with B, whatever that interval is, chop it up into equal bits. So to get the height of each rectangle, we're going to take some value c sub I in between these two numbers and plug it in, and then whatever the value of the function is at that, we're going to call the height of the rectangle. So the rectangle will go up to some point on the function in the subinterval. The base of each subinterval is always going to be delta x. We're going to make all these equally sized, the bases. And so to do that, here's our formula. The width of each rectangle is called delta x, and it's going to be b minus a over n. So whatever the width of the whole thing is divided by however many rectangles we'll be using. And then we'll get the heights by plugging the value c sub I into our function. In the examples we're doing, I think we'll always use either left endpoints or right endpoints. So actually all these c sub i's will either be these values or these values. And we'll see how that goes a little more when we get to an example. So let's do an example, and we'll see how this goes. So let's talk about this in terms of delta x and c sub I once we get there. So we can actually draw a picture of this, so maybe we should do that. Let's see what we have. We're going from 0 to 6, so we'll call this 0, and we'll call this 6 on the x-axis. That's here. This is the function y equals x squared plus 1, so remember what that looks like. This is the basic parabola, and then we're adding 1, so we're shifting it up 1. So let's see, 3 intervals, so so this will be 1, 2, 3, 4, 5, 6, and so let's put 1 here. So we've shifted it up 1. This will not be exactly to scale because notice if I plug 6 into this, I should be at 37. So we're just going to put, so it's increasing pretty quickly, but we want to stay in frame, so I'm just going to do that. Okay. Keeps going that way. So this is y equals x squared plus 1. Okay, so let's notice what we have here. So we have some information. Tells us the number of rectangles, so this is n. So n equals 3. This is my a and b. So b is equal to 6 and a is equal to 0. And then my function f of x is just going to be x squared plus 1. Okay, so this is all the information we need to fill out the other stuff. So first let's start with computing the widths. So all the widths are going to be given by delta x. And it's b minus a over n, which in this case is 6 minus 0 over 3. So that's 6 over 3, which is 2. So the width of all of our rectangles will be 2. So we can go ahead and put those in here. So starting at 0, we're going to just fill in our rectangles, all having a width 2. So the first one starting at 0 ends at 2. The second one starts at 2, ends at 4. The next one starts at 4, ends at 6. And there's the 3 bases of our rectangles. So how do we get our heights? So our heights are going to be given by plugging something into the f of x, which is x squared plus 1. So first, let's see what our sample points are going to be. They're going to be given by our left endpoint. So we're going to take the left endpoint of each subinterval. And our subintervals are here, 0 to 2, 2 to 4, 4 to 6. So C sub 1, we need a C sub 1, a C sub 2, and a C sub 3. So we need a sample point for each rectangle. So C sub 1, if I'm on the interval 0 to 2, the left endpoint is here. So this is going to be C sub 1 is 0. C sub 2 is going to be the sample point for my interval 2 to 4. The left endpoint is 2. And then C sub 3 is the sample point for my third rectangle, and the left endpoint is 4. All right, so these are the values I'm going to plug in. And then how am I going to get those? I'm going to just plug them into my function, which is x squared plus 1. So I'm going to get 0 squared plus 1. And then plug in 2. This will be 2 squared plus 1. And then plug in 4. F of 4 is 4 squared plus 1. So there's 1. This is 4 plus 1 is 5. This is 16, so this is 17. Okay, so here's our widths, and we're going to have 3 different rectangles, and they'll have 3 different heights, and there's our heights. So let's see how this looks on the picture. So when I plug in 0, I get 1. So that's telling me this, that the height of the first rectangle looks like this. So here's my first rectangle. There's R1. My second rectangle, I'm going to plug in 2, and this should be up at 5. So notice this is not to scale again. So it's crammed down just because this function increases so quickly. We need to sort of adjust the scale. So pretend that's 5. And then when I plug in 4, I should get 17. So this really should be jumping up to 17. And so that's the height of my third rectangle. Okay, but then to compute this area, you don't need this picture. I just wanted to draw it just to have something to go along with it. The area is just going to be the areas of each of these rectangles. So 1 times 2 plus 5 times 2 plus 17 times 2. So we can just compute it this way, right? This will be 2 plus 10 plus 34. And so that's 36, 46. And so this is the answer. So this is what we're looking for. So this is the approximation of the area under here using left endpoints and 3 rectangles. Another thing you should notice here is there's actually a maybe sometimes a shortcut. Notice that since the width is always the same, I can factor this out. So it might be actually easier to compute it this way. Right, so in this case it'd be 6 plus this is what, 23 times 2, which is 46. So either way you do it, you can either add up all the heights and multiply it by the width, or do each rectangle individually.